Welcome back. The previous lecture we had seen the proof of fundamental theorem of algebra as a culmination to looking for roots of polynomials of degree n. In the proof of the fundamental theorem of algebra we had used the Cauchy integral theorem. So our aim is to now use that as an opportunity to go and venture into complex analysis and look at the proofs of some of these important results from complex analysis. So to begin with, today we will look at complex numbers and complex maps. Okay. So to start looking at complex numbers and complex map, let's start with the definition of a linear map. This you must have seen in your course in linear algebra. So if you have two vector spaces V and W over the same field F, then a map from V to W is said to be linear if this property here is satisfied for all scalars alpha beta from the field and all the vectors x and y from V. This is the definition of linearity. And further to this, your linear algebra also tells you that if V and W are finite dimensional is vector spaces, then every linear map can be associated with a matrix. So the way this is to be understood is that if V and W are finite dimensional, say of n and m respectively, and there is a specific basis chosen for both V and W, then with respect to that you can have a matrix representation for the linear map T, and this matrix dimension is m cross n. Fine. So there is a one-to-one correspondence between linear maps and matrices, and the dimension of the range of T is called the rank of T, and the dimension of the null space of T is called the nullity of T or nullity of A. And the rank and nullity theorem tells you that the dimension of V is the sum of the rank of T and the nullity of T. In fact, in linear algebra, you learn all these things finally as a need or as an attempt to solve a system of linear equations. So in the previous two lectures, what we have seen is algebraic equations which were polynomials. Now, system of linear equation is also an algebraic equation, but with more than one unknowns and hence more than one equations. Right? Now, linear algebra gives you a way to solve these things under certain conditions and so on. So the rank and nullity theorem actually tells you tells you the situation of when you have a unique solution, more than one solution, or no solution, etc., depending on the relation between m and n and so on. That's part of linear algebra. Okay, so we will not get into that subject in this course now. So the reason for going into linear maps is to understand. So let's look at an example. So what are the linear maps on the real line? So let's take V to be R and W to be R. Okay, so V is R, W is R, both are vector spaces of dimension 1, that is M and N are 1. And from this result, we know that every linear map from R to R is actually a 1 cross 1 matrix, which means 1 cross 1 matrix is just a real number. So every linear map can be given as a real number multiplied with the argument. That's what this result says. So the linear maps from R to R can be associated with real numbers. Okay. Yeah. Okay. So that's what we are saying here. I have given a graphical representation here. Here in this picture, I have just shown all possible linear maps in one picture. So each color represents one linear map. So what is this saying? That every linear map from R to R is actually a real multiple of X, whereas where this alpha actually relates to the slope of the graph of that map, right? Slope of that line, right? Linear maps are line passing through origin. So alpha gives you the slope of that map, right? And the angle of inclination is tan inverse of alpha. So you have this connection between real numbers and linear map, which means that one can think of real numbers as linear maps, one can think of linear maps as real numbers, right? And the property about this linear maps on real line is that it dilates points, right? You can see that from the definition here. Any x is taken to alpha x, which means depending on whether mod alpha is bigger than 1 or smaller than 1, the point is either stretched or shrunk, right? So when mod alpha is bigger than 1, x goes to alpha x is actually stretching x to alpha x. When mod alpha is less than 1, then the point x is shrunk to alpha x. When mod alpha is equal to 1, it just fixes the point, right? And when alpha is the minus 1, then it reflects the point, whatever. So basically linear maps on R dilates points. This is a property of the linear maps on R. Okay. Keeping this in mind, now let's look at complex numbers and ask the question, what are the linear maps on complex number? Again, by the previous theorem that we saw in the previous slide here, if I take V to be C, a vector space, over C, which is of dimension 1, and W also to be a C, a vector space, over C, which is also of dimension 1, then this property actually tells you that every linear map is actually given as a 1 cross 1 complex number multiplied, right? So every linear map from C to C is a complex number multiplied to the argument, right? The same uh, with the same explanation that we gave some time back. So let's see that here. So if I take any complex number omega, associated to this complex number, I can give a linear map defined as the complex multiple. So the argument multiplied with the complex number omega. Conversely, if you give me a linear map, then I look at the image of 1, I define that as omega, and t of omega will be defined for this omega. So any complex number defines a linear map. Every linear map is actually given as a complex multiple for some complex number. So you again have the same association that every linear map and complex number is nothing but the complex multiples like you had in real number. But the difference comes after this. In the real number, the linear maps were dilations, right? Whereas in complex number, the linear maps are going to be rotation and dilation. How do you see that? So let's first understand what is complex multiplication, right? Because that's what we are using here, right? This is complex multiplication. In the real case, you had an alpha x, it was a real multiplication. So in complex multiplication, so what does complex multiplication do? Look at this. Take any complex number omega, its real part is x, its imaginary part is y. Take any complex number z, its real part is xi and its imaginary part is eta. So if you multiply omega and z, it is multiplying these two real numbers. You get the real part to be this and you get the imaginary part to be this. I have just written this in the vector form instead of the complex form for a reason that you will notice now. So the complex multiplication of these two complex numbers is this complex number. This complex number can also be seen as this matrix acting on xi and eta. Right? So this matrix acting on this is precisely this. So this complex multiplication can be seen as this map acting on xi eta, and xi eta is precisely the complex number z, and xy is precisely the complex number omega, which means this is a matrix associated to omega. In fact, what you see here is that every complex number can be associated to a matrix like this, a 2 cross 2 matrix. So if you have a complex number with real part x and imaginary part y, and if you write down this matrix, putting the real part on the diagonal and the imaginary part on the other diagonal here with a negative sign here, this you can associate a matrix like this to every complex number, and what is complex multiplication is precisely this matrix acting on that vector. But what is this? This is a linear map on R2, right? This is a 2 cross 2 matrix. 2 cross 2 matrix we have. So your linear algebra says the same theorem that I have been using in the first slide, that any linear map from R2 to R2 will be given by a 2 cross 2 matrix. And this is saying this is a special class of 2 cross 2 matrix where the matrix looks like this, right? So what is this? Whatever we have here, this equation is telling is that every complex number can be associated to a special linear map on R2. But every complex number is also associated to a linear map on complex numbers. So in turn, every complex linear map can be associated to a special form of linear map on R2. What is the special form of linear map in R2? They are precisely the rotation and dilation in R2. These matrices, if you notice, are actually the rotation matrices. This R is the dilation constant. So every complex number or every linear map on the complex number can be associated to a subclass of real linear maps. So this is not the full class of linear maps, right? This is a sub collection of linear maps on R2. So every complex number can be associated to a sub collection of linear maps on R2, which are precisely the rotation and dilation matrices. Right, which basically kind of says that every complex number is associated to rotation matrix, which means complex multiplication basically means that you are doing a rotation and dilation. So in the real numbers case, you were actually dilating points. In the complex numbers, you are rotating and dilating points. Okay, so this is the difference between real and complex numbers. So from this, one can understand further. So we can also see the same result in a different perspective. If we write any complex number in the polar form, that is magnitude and argument, using the Euler's formula, right? Because every z has an x and y, real part x and imaginary part y. If you write in the polar form, x has r cos theta and y has r sin theta form. Because it's you are in the complex plane, this is actually r cos theta plus I r sin theta, which is precisely by Euler's formula this one, right? So if you write this in the polar form, and if you take another complex number w also in the polar form, and if you multiply them, what you get in the multiplication is this. That is, what is this saying is that if you take a complex number z and if you multiply it with a complex number w or omega, what it means is that the z vector is rotated by the argument of w and dilated by the magnitude of w. So rotation and dilation, that's what complex multiplication does, right? So there is a connection between complex numbers and the rotation dilation matrices on R2. Now this connection is very important, and this is what brings the major difference between real analysis or analysis on R2 and complex analysis. That is this. Let's say the notion of derivative, right? When we say derivative, what we are doing is that we are linearly approximating the graph of a function, right? We are looking for a linear approximation to the graph of a function at a point. So when we say complex linearity, it is a much more stronger requirement than when we say linearity in R2, right? Because we had associated complex linear maps to a subclass of linear maps on R2, which means complex linearity is a stronger condition, right? This you can see easily from this definition itself, right? Because when you say complex linearity, you are going to take scalars from the as from the complex numbers, and you want this t of the scalar multiple to respect the so the so t should respect the scalar multiplication. But complex numbers includes real numbers. So this automatically implies that anything that is complex linear is also real linear, which means that complex linear is actually a smaller collection than real linear, right? So when we see R2, when we see linear maps on R2, we see R2 as a vector space over R of dimension 2, whereas C is seen as a vector space over C of dimension 1, right? So in that sense, complex linear maps are a much smaller collection than linear maps on R2. This basically means that when we give a notion of derivative in the complex plane, what we are doing is we are looking for a complex linear approximation to the complex function at any point. Now that is a stronger requirement than asking for total derivative of the same function in R2, right? Because complex linear is a much more restrictive condition. So looking for complex derivative is a stronger requirement. As an example, if you take this conjugate map, z goes to z bar, which is actually the reflection along the real axis, this is not a complex linear function because it will not respect the scalar multiplication, right? You can see that alpha times z will be alpha bar z bar, which is not what linearity tells you. So this is not a complex linear map. While the same map in R2, which is precisely x comma y going to x comma minus y, this is the reflection along the x-axis, right? The same map as the conjugate map. This is a real linear map, whereas the same function in complex plane was not linear, which means that if I want to differentiate this, x comma y going to x minus y is differentiable because it's a linear map. So the linear approximation of such a map will be itself. So it's a differential map, whereas the complex valued function, which we will see later, is not differentiable anywhere, right? So you see the difference between the linearity in the complex plane and the linear functions on R2. The linear functions on R2 are a much bigger collection, whereas the linear functions on complex numbers are a much smaller collection, which is what gives you these nice properties of this complex differentiable functions, which we will see later. Okay, I hope you see these connections and you understand and you appreciate these connections. Now, how do we visualize functions in the complex plane? For instance, when I have a function from R to R, I can visualize the function as a graph in R2, right? Whereas the graph of a function from C to C is actually a subset of R4, which is not easy to visualize. I mean, not easy for, I mean, we cannot visualize a R4, 4 dimensions, right? Something sitting in 4 dimensions. So how do we do this? The idea is to look at what happens to specific subsets of the domain or curves in the domain. So whenever you have a map from C to C, if it's an injective map, the nice thing to do is to see what happens to lines and circles. So where are lines mapped, where are circles mapped? Looking at these things will give you an idea of what the function is doing, some kind of visualization of what the function is doing, right? And when we say line and circle, in fact when we say line, we can also think of line as a circle passing through infinity. Okay, that is a, I mean, you can think of that. It's you can think of line as a circle with infinite radius. Okay, how do we see that? If you look at the complex plane, right, and with uh, with say infinity, if you think of infinity as one more point, and the complex plane with infinity can be made a, one can make a one-to-one correspondence with the sphere in R3, right? So you map the infinity point to the north pole of the sphere, which is the 0, 0, 1 point here, and then every other point on the sphere can be uniquely associated with the with a complex number, right? The way you do is that you take a complex, you can imagine the complex plane as cutting across the I mean, in the middle of the sphere. Then you take any complex number on the complex plane, and then you join it with the north pole. The place where it intersects the sphere is the point that corresponds to this complex number. Okay, so except the north pole, everything is mapped to the complex plane, and the north pole is mapped to the infinity. In this sense, you can see that any line here, any line on the complex plane can be seen as a line passing through the north pole here. Okay, and if you have a map which is not injective or if it's multi-valued, then these can be visualized using the concept of Riemann surfaces. Okay, multi-valued functions naturally occur in the complex domains. Okay, and they are also useful. So the way to understand multi-valued function is to introduce a branch cut, and you restrict your function to within some region between branch cuts, and there the function will turn out to be single valued, and then it becomes, you can study all the properties and you can see it as a function and so on. So the way you can visualize these things is that you can see the multivalued function as defined over different regions or strips and so on, divided by branch cuts. So you have so you patch up surfaces along the branch cuts and so on. So that is how you understand these things. So as an example, let's see how we visualize complex functions. So let's look at the function z square, which is whose real part is x square minus y square, and its imaginary part is 2xy. This function is not injective. You can see that, right? Because if I take a number, if I take a complex number with positive real and another number with negative real without changing the imaginary part, then the square is going to be same in the real part, whereas the sign is going to change in the imaginary part, right? Same with the other y part as well. So if you look at what this map does, so the way we can visualize this map is like this. You see, if you take the imaginary axis, which is in the brown color here, the imaginary axis means that it is x equal to 0. So x is 0 here and x is 0 here. So you don't have any imaginary part in the image domain. You have only minus y square here. So you take any y here in the imaginary line, it gets mapped to minus y square. Y square is positive, so minus y square is negative. So basically this image, so this imaginary line gets mapped to the negative real axis here, and both. So you see, because minus y square, if you take negative y's, also gets mapped to the negative. And so basically this line here splits here in the middle and then gets mapped to the negative real axis. And if you look at the real axis here, which is y equal to 0, then again your imaginary part is 0. What you have is just x square. So the entire real line here gets mapped to the positive real axis here. Okay. Now you look at all these red lines, which are the vertical lines. Okay. And these vertical lines get mapped to these parabolas here, the red parabolas here. The last one here I've shown the yellow, which is this yellow line here. So all these parabolas here and here, right? All these red and yellow parabolas is precisely these vertical lines getting mapped here, right? Natural, right? Because in these vertical lines, what you have is your x is constant, your y is varying. Since your x is constant, you get some constant square minus y square plus 2 constant y, right, in the imaginary part. So what you get is this these curves here, right? Now that is right, you can see that, right? So this part here is the real part of z square, this is the imaginary part of z square. So the real part is this, the imaginary part is this. So you plot that graph. Similarly, you look at this horizontal blue lines, they again get mapped to this parabola, blue parabolas, right? Here what you see again is that here again you see that the value of y is fixed, only the x is changing, but here the values are negative y's and here the values are positive y. So for negative and positive y, the real part doesn't change, what changes is only the imaginary part. So these lines in the negative with negative y's comes from below here and joins the parabola here, and the lines above comes from the top and joins at this point here. So you see here this green line here is this gets mapped here, and this line here is actually kind of magenta cyan color is actually gets mapped here, right? There is also another interesting property to this map here. If you see here, these blue lines and red lines intersect each other orthogonally. The point of intersection has angle 90 degrees. You see this is also preserved here. The blue parabolas and the red parabolas intersect orthogonally. Their point of intersection, the angle is 90 degree. Okay. Now such maps are called conformal maps, which you will see at the end of this lecture. So this is actually an example of a conformal map, because I mean we have not shown it completely. We have only have one set of one family of curves, but this happens for every curve on the domain. Okay, so this is how you visualize complex functions. This is a function, exponential complex function. The exponential complex function is defined using the power series in the complex plane. Okay, so this is again not a injective function, and more than one point gets mapped to the same point. For instance, if you think of e power, if x and y are the real parts of z, then e power z is this. If you think of this in the polar form, so e power z has the magnitude e power x and the argument y, right? Now here, from here you can actually see that if I take any z and add I to pi k for any integer k, then that is same as e power 2z, because iy plus 2 pi k is same as iy. So there are infinitely many points which gets mapped to the same value. So if you look at this, if you want to visualize this, you actually see here that in for this map, if you look at this this imaginary line gets mapped to the unit circle, right? Because in the imaginary line the x is 0, x component is 0, so this x is 0, so it's e power 0, which is 1. So e power z for imaginary line is just e power iy. So, and e power iy is on the unit circle. So the imaginary line gets bent and it gets mapped to the unit circle here. And what happens to the real line here? The real line here is y equal to 0, which means angle is 0 angle, and the magnitude is e power x, okay, which is again here. Now the point that we try to see here is that if you, as I said, imaginary axis gets mapped to the unit circle, and all the points on the left hand side of the imaginary axis, that is the left half plane, gets mapped inside the unit circle, and the right plane gets mapped outside the unit circle. All these vertical lines here gets mapped to circle, right? All the vertical lines on the left side gets mapped to the circles inside the unit circle. All the vertical lines on the right half plane gets mapped to circles outside the unit circle. All these horizontal lines gets mapped to these lines passing through origin. Okay. Okay. So this is how you can visualize things, and here you actually see that you can actually see that the domain, if you take the full complex plane here, you have this many to one function. So if you restrict yourself to say minus pi to pi domain, you actually have a injective function and so on. Okay, that is how you can imagine these things. Anyway, now let's look at the inverse map 1 over z. Okay, this 1 over z do? In fact, what 1 over z does is that it actually reflects along the about the unit circle. Okay, for instance, it's not defined at the point z equal to 0, but if you see the complex plane in the Riemann sphere sense, then you can say that at z equal to 0 it gets mapped to infinity. So this map actually inverts about the unit circle. Okay, the way you can see that is that 1 over z can be 1 over z can be seen as z bar over mod z square. Okay, so z by mod z square is basically the reflection on the unit circle, and z bar is the reflection along the uh, real axis. Okay, so the one nice property about this map 1 over z, is that it preserves the family of lines and circles. What I mean by that is that if you take lines or circles, and the image of that under 1 over z is also a line or a circle. What I mean by that, I'm not saying that lines get mapped to lines and circle gets mapped to circle. I'm saying that lines can get mapped to lines and circles, circle can get mapped to lines and circles. Basically, the family of lines and circles are invariant under this map. Okay. So how do you see this? That so the equation for lines and circle is this. okay, where this condition that b square plus c square is bigger than 4ad. If a is 0, then this is the equation of a line, and if a is 0, then this condition becomes b square plus c square strictly greater than 0, which basically means that both b and c cannot be 0 at the same time, which gives sense to the meaning to this equation of line. Okay, so what we need to check is that the image of this family is also this family, the same family. Now use this fact that because any x and y, if x and y are the real and imaginary part of a complex number, then the real part is z plus conjugate of z over 2, and the imaginary part is z minus conjugate of z over 2y, right? Use that fact and rewrite this in terms of z. So this equation here is precisely this equation here, what you have here, right? Now what is the image of this? So what is the image of that? Suppose we are looking for the image, say w, then what are we looking for w? W is such that 1 over w satisfies this equation. So if 1 over w satisfies this equation, then w satisfies this equation, which again, using the fact that if w has a real part u and v, then you can write it in terms of its real part. So this equation becomes this. So the image of this ax square plus y square bx cy d equal to 0 is du square v square plus bu minus cv plus a equal to 0. Now, which means that the family of lines and circles gets mapped to itself, right? It is also an equation for lines and circles. Let's see one by one what happens in each case. So if you take a line passing through origin, it basically corresponds to the case when a is 0 and d is 0, because when a is 0, d is 0, it's a line passing through origin. And what is the image of that? D is 0, a is 0, so it's a line passing through origin. So the image of line passing through origin is a line passing through origin under the map 1 over z. Similarly, the image of line not passing through origin, which means that only a is 0, okay, it's a line, so a is 0, so this equation bcd is available. Image of that means a is 0 is actually a circle passing through origin. So image of a line not passing through origin is a circle passing through origin. If you relate this with the notion that I told you about thinking of line as a circle of infinite radius or circle passing through infinity, this is what it's saying, that a circle passing through infinity gets mapped to a circle passing through the origin, right? Because origin and infinity are mapped to each other by this map, right? Similarly, the image of a circle through origin means d is 0, image of a circle through origin gets mapped to a line not through origin. Similarly, the image of a circle not through origin is a circle not through origin. Okay, so line not through origin is line not through origin, circle not through origin is circle not through origin, and the other cases. Okay, so this is a property of this inversion map. So it preserves the family of lines and circle. But this is actually not something very new in the sense that you didn't need 1 over z to tell you about these functions. There's a reason we consider this, but then even your linear maps that you started with, complex linear maps, right, az or even az plus b, right, even these satisfy these properties, right? For instance, if you take this map az plus b, this also preserves the family of lines and circles. Why? Because we have already seen that complex multiplication is rotation and dilation, plus b is translation. So this map is precisely can rotate, dilate and translate. If you take any line or a circle, if you rotate, dilate and translate, you are going to get a line or a circle, right? So this map also preserve. You can also give a proof like the previous slide proof. Okay. So we have a collection of functions here which preserves family of lines and circle. We also had this 1 over z which does the same thing, but 1 over z does not belong to this class of functions here as az plus b here. So combining these two, we actually have what is called the fractional linear transformation or fractional linear maps, which is the composition of these two maps, right? Because see, you see, if I have two functions and both preserve the family of lines and circles, then the composition will also preserve the family of lines and circles, right? So if we compose a function like az plus b with a function like 1 over z, more generally it turns out to be what are called the fractional linear maps. Okay, here we impose this condition that ad minus bc is non-zero to exclude constant functions, right? For instance, if I take a constant, for instance here, if when a is 0, fz is a constant function b, there is nothing is happening, I mean it's not preserving line and circle, right? It is all lines are going to a point and so on, right? So of course you can think of point as a circle of 0 radius, but that's another way. So if you exclude these points, then sorry, if you include this condition, then you exclude a constant function as possible maps here. And the proof that this map also preserves family of circles and lines is similar to what we saw in the previous slide, using the equation of line and circle and look at the image what happens. The other way of looking at series, since we have already done the proof for 1 over z, the other way of looking at is that this fractional linear map is actually a composition of linear map and the inverse map, right? Because for instance, in this function here, if you add and subtract ad over c in the numerator here, you add and subtract ad over c, then the b minus ad over c is coming here. So there is a az plus ad over c. You multiply and divide by c here, so you get acz by c. Take a over c common out, so what you get is a over c times cz plus d and then this. So the cz plus d in the denominator and the cz plus d in the numerator here will get cancelled. So this f is precisely this map, and the reason why we have rewritten this map like this is to easily to kind of help you see that this is actually composition of this linear map and the inverse map, right? And we have already shown that both of them are preserve family of circles and lines. So this composition also preserves family of circle and line. Now these fractional linear transformations are actually a special class of functions of this general class called conformal maps, right? So what are conformal maps? Conformal maps are maps which preserve angle between curves, right? So what is the angle between curve? If you have two curves intersecting at a point, then the angle between the curve is precisely the angle between the tangents at that point, right? So the precise definition of conformality is this, like your continuity and derivative definition. Conformality is also a local definition. It is defined at a point. We say it's conformal in a region if it's conformal at every point in the region. Okay. So a map f from C to C is conformal at Z0 if for any curve that you take which passes through Z0, there is an angle theta and there is a scaling r, and both these theta and r depend only on Z0 and not on the choice of gamma. Okay, such that f rotates the tangent vector at Z0 by an angle theta and scales it by r, dilates it by r. Okay. This is what the definition of conformal is, right? So here you see that this at z naught you get a theta and r, which can change only if you change the point z naught. But at z naught, whatever curve that you take passing through z naught, this is not going to change. As a consequence of this, you immediately see that such a map will preserve angle at z naught, right? Because if I take two different curves, gamma 1 and gamma 2 passing through z naught, right? According to the conformality, I have a theta and r, right, for both gamma 1 and gamma 2. So the tangents of gamma 1 and gamma 2 at z naught both will be rotated by the same amount theta and r, which means the angle between both the tangents will be preserved, right? Another way of looking at this conformal map is that a map is conformal if f multiplies all tangent vectors at z naught by a complex number. Now this is again something you should be able to see it easily, because we have already seen that every complex number, every complex multiplication is rotation and dilation. And what conformal definition at z naught is doing is that this map f is actually rotating the tangent vector by an angle and then dilating it by r. So there is a rotation and dilation happening, which means f rotating the tangent vector basically means that it is multiplying the tangent vector by a complex number. What is that complex number? Precisely r e power I theta, right? This r I dilation and angle theta. So something is conformal at z naught if f multiplies all tangent vectors at z naught by a complex number r e I theta. And for examples of conformal mapping, there are a lot. So when we define the notion of holomorphic function and so on, in fact, this is true for analytic functions as well, right? So if a function is holomorphic at z naught, such that its derivative at z naught is non-zero, then that function is conformal at z naught. I mean, I missed here saying at z naught, it is conformal at z naught. The reason proof is very simple, because if I take any curve gamma on the domain, then the image is the curve f composed with gamma, and the tangent vector at that point is precisely the derivative of that, which by chain rule is f prime z naught gamma prime t naught, right? Which means there is a complex number f prime z naught multiplied to the tangent vector at gamma, right, where gamma t naught is z naught, right? So whenever this is non-zero, you see whatever gamma you take, it's always the f prime z naught that is multiplied to that tangent vector. Okay, so any analytic function or any holomorphic function is conformal. This is an example of so there are lots of examples of, like the one we saw, z square, z going to z square example that we show, and in fact I even mentioned there that the horizontal and vertical lines were mapped to parabolas and the angle between them were preserved, right? Same even in the e power z example, though I didn't mention there, in the e power z example that I showed you, even here the angle is orthogonal, and they here again they meet orthogonally, right? So e power z, z square, all these are conformal maps. Special case, as I said, fractional linear maps are also conformal maps. Now what is an example for a non-conformal map? The conjugate function is not conformal. In fact, what does conjugate function do is that it reflects the points along the real axis. So what it does is that it actually doesn't change the length of the tangent vector and so on, because it just reflects it. What it does is it changes the orientation of the tangent vector, and that is why it fails to be conformal, because by our definition of conformality, you should also be preserving the orientation, right? So that is an example of a non-conformal map. So with this, I think I hope you got some idea about how to visualize complex numbers, complex maps, what are the geometry that lies behind complex numbers and complex linear maps, and so on. This intuition helps a lot when you work and when you do some problems and when you face difficulties and so on. So I hope you appreciate whatever is done in this course and you have learned something new. Thanks a lot. Bye.